going to talk about the origin of life. Now, it won't have escaped your attention that 150 years ago, Charles Darwin published his famous book on the origin of species. And in that book, he gave a convincing account of how, over billions of years, life on Earth has progressed from simple microbes to the richness and complexity of the biosphere that we see today. But he pointedly left out of account how life got started in the first place. In fact, he said it is mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter. Now, it's curious that in the last 20 years or so, physicists have explained the origin of matter. It's no longer a problem. We know how matter came to exist in the universe. We still don't know how life came to exist. 150 years later, we're not very much further forward than Darwin was in understanding how life came to exist in the first place. The theory of evolution, which we're, I guess, on this boat to celebrate, of course, only kicks in once life gets started. Can't really help us understand that first step, how life arises from non-life. So that's what I'm going to talk about this evening. And it's really three problems all wrapped into one. There's the when, the where, and the how. The when part, we are making a lot of progress on. The where part is still a little bit uncertain, but we have some good ideas. And as we shall see, the how part remains deeply problematic. Let me just basically deal with the when part as quickly as I can. Life established itself on Earth a long time ago. Darwin himself was aware of fossils that went back, well, we now know about 500 or 600 million years, but was puzzled why rocks older than that seem to contain no fossils. Well, they're there all right. It's only that before about 600 million years ago, life on Earth was single-celled only, and so the fossils preceding that time are fossil microbes, or microfossils. And if you look carefully around the Earth, you can find rocks dating back to about 3.5 billion years, and those that contain the oldest traces of life on Earth, reasonably uncontested, are these rocks here, jutting out of this hillside, in a region of Western Australia known as the Pilbara. And for those who haven't been there, there's a map of Australia, and the Pilbara is up in the northwest there. It's in the province or the state of Western Australia, about a 4-hour drive inland from Port Hedland. And Pauline and I took the trouble to go there some years ago. That's to prove I've really done it. You see that the terrain is very arid. It's a hot, dry part of Australia, a little bit like Arizona, in fact. And the reason people, or the scientists, make their pilgrimage to these particular hills concerns rocks like this. As you see, it's very hot. And the rocks are called chert. And if you look at those rocks, there are these little features which are rather like ice cream cones stacked together and sliced through. Now, to you and me, they probably just look like features in a rock, but geologists get very excited when they see these because they believe they are fossilized stromatolites. Stromatolites. Now, what is a stromatolite? It's not a living thing, but it is a structure, a mineral structure, built by microbes. This can be seen even today, although living stromatolites are really hard to find, but about a 2-day drive from this same region of Western Australia, you head south, you arrive at a place called Shark Bay. There it is. And here you will see the living stromatolites, these sort of leathery mounds. So they don't look really up to much. But if you imagine getting in a time machine, I was talking about that last night, going back 3.5 billion years and stepping out, this is about all you would see. Life on Earth just looked like that 3.5 billion years ago. As you can see, pretty boring compared to what's going on today. So these stromatolites, I guess they have their own intrinsic beauty, but they're not the sort of things you will want on your living room mantelpiece. They're just like little leathery mounds, and they consist these days of cyanobacteria, which sit on the surface, they photosynthesize, and they deposit these mineral layers. If you come back in another 3 billion years, you can imagine that they would be fossilized like the ones I showed you earlier. Now, if it were just the fossilized stromatolites alone, probably people would be not very impressed as to evidence for the oldest life. But also in the same region of the Pilbara Hills, these microfossils have been found. And so these look a little bit like fossilized cyanobacteria, but it's really hard to know. And again, they date from 3.5 billion years ago. So to put this in context, in case anyone here doesn't know, the Earth is a little over 4.5 billion years old. The fact that we have traces of life on Earth going back to 3.5 billion years shows that there's been some form of life on this planet for most of its history. And of course, what interests me is how did it start up in the first place? Now, I've said that Darwin wouldn't be drawn about how life began. That's not entirely true. In a letter to a friend, he did conjecture about what he called a warm little pond. And here it is. A warm little pond in which, over a period of time, all sorts of minerals and chemicals would leach out of the rocks as a result of the rain and would accumulate in the pond. And then under the action of sunlight as an energy source, eventually these molecules would become more and more complex, and through an extended period of spontaneous complexification, eventually something would crawl out, some living thing would form inside this warm little pond. And that became the basis of what was known as the primordial soup theory, the idea that there is a watery medium somewhere on the Earth in which some sort of chemical magic that nobody quite understands would have taken place over a long period of time. Chemical self-organization would have led to some simple living thing. So the primordial soup theory has been the main theory ever since Darwin came up with this idea. However, the notion of the warm little pond really doesn't now seem very realistic. And the reason for that is that we understand much more than Darwin did about the conditions on the early Earth. Now, the solar system formed, as I said, about 4.5 billion years ago from a gigantic cloud of gas and dust. Probably the sun formed along with many other stars at the same time. And this cloud of gas contracted slowly under its own gravitation. And because it would have been slowly rotating, as it shrank, so it spun faster and faster, a bit like the ice skater who draws in her arms to spin up. And so that would have led to a configuration with the proto-sun at the center and a swirling cloud of gas and dust around it. And from that cloud of gas and dust, the planets formed over a period of some millions of years. Now, this obviously didn't happen overnight. This is an artist's impression of the formation of the planets out of this gas and dust swirling around the sun. What happened was that out in the periphery of the solar nebula, ice crystals formed, and these are quite sticky, as we know from making snowballs, and the dust and the ice sort of stuck together to form dirty snowballs, and these gradually accumulated until their own gravitational pull became significant, and they dragged in more and more material, and eventually formed the giant planets out in the outer region of the solar system, like Jupiter and Saturn. In the inner regions, the more refractory material with a higher melting point, congealed to form the planets like Mercury, Venus, Earth, and Mars. And these planets eventually began to suck in material from the surroundings as well. And so there was a period of about 700 million years when the early Earth was being ferociously bombarded by all manner of debris, from small grains of sand right up to enormous objects hundreds of kilometers across. This is an artist's depiction of this period of early bombardment. Now, the granddaddy of all impacts occurred shortly after the proto-Earth formed, when it was struck by a Mars-sized body. And this body ploughed on into the center of the Earth and became the Earth's core, and stripped away a lot of the material from the outside, from the periphery, that congealed to form the Moon. So it's now believed that the Moon is a result of this awesome cosmic impact that occurred early on in Earth's history. Now, these big impacts were awesome in their destructive power. A typical large impact might have been an object up to 500 kilometers across. If an object like that hit the Earth today, it would excavate a crater about half the size of Europe, it would strip away much of the atmosphere, and it would swathe the planet with incandescent rock vapor, which would have a temperature enough to boil the oceans dry. So the whole Earth would be coated in a sort of superheated steam rock vapor atmosphere, which would effectively sterilize everything on the surface. And we believe that there were dozens of such impacts up until about 3.8 billion years ago. The reason we know that is because if we look at our near neighbor in space, the moon, we see evidence of bombardment down at every scale of size. Of course, it's well known that the moon is heavily cratered. But these dark areas here, like Mare Crisium, which is the one that's indicated, astronomers used to think that they were seas. They're called maria. They're not seas at all. They're impact basins from these massive collisions with cosmic bodies. And because the Apollo astronauts went to the moon and brought back rocks, they can be dated. And so we now know that these impacts producing these smooth areas occurred up until about 3.8 billion years ago. So the scene on Earth would have been something like this, sound like something out of hell, because of the enormous heat energy released by these impacts, so boiling the oceans. So we obviously have a problem for warm little ponds because of the serious disruption that would occur. They wouldn't be left there for a long period of time. So this leads to a bit of a paradox, because on the one hand, the record of life on Earth stretches back 3.5 billion years. And of course, it wouldn't have just popped up ready-made. There must have been an extended period of evolution leading up to the Pilbara microfossils. And so we might want to trace the origin of life on Earth back to getting on for about 4 billion years ago. But the heavy bombardment continued until about 3.8 billion years ago, and then it began to abate. Of course, it never stopped entirely. As we know, the dinosaurs were done in 65 million years ago by an impactor probably about 20 kilometers across, and even today there is a persistent threat of asteroid and comet impacts. It hasn't gone away, but it's far, far less than it was in those early days. So that leads to a bit of a problem. How was it that life appeared on Earth more or less with the end of this heavy bombardment? Now, one possibility, of course, is that life didn't start on Earth. Darwin assumed that life on Earth began on Earth, and that seems like the natural assumption. But we have no reason to suppose that. It could well be that life started somewhere else and came to Earth. And you might wonder where else. And everybody's favorite is the planet Mars. Mars is smaller than Earth, so cooled quicker, was ready for life sooner. And it's entirely possible that there was life on Mars, say between 4.5 and 4 billion years ago. Now, one of the things that is very clear today, though it wasn't when I got interested in this subject 20 years ago, is that if you have life on Mars, you very soon have it on Earth. And the reason for that is told in the next picture. I think makes the point very well, that Mars, just like Earth, gets pounded by asteroids and comets. It was much more ferocious in the past. And the biggest of these impacts has the power to splatter Mars rocks all around the solar system. And some of these rocks eventually hit Earth, and we know that because I'm holding one here. There are about 50 Mars meteorites that are currently known. There'll be many more. You might even have some in your back garden. You can't tell by looking what they're made of, but with careful analysis, you can identify that some meteorites originate on the planet Mars. There's no doubt whatever that is the case. And so this raises the possibility that if you have life on Mars, that microbial life cocooned inside rocks blasted off Mars by asteroid and comet impacts could hitch a ride and come to Earth inside those rocks, protected from the rigors of space. It would take me too far beyond the scope of this lecture to discuss the hazards that they face. Obviously, it's not an easy journey to be blasted off a planet, to go into the cold and vacuum of space, to endure the radiation hazard of space, and then to survive entry into the Earth's atmosphere. But when you look at all of those things in detail, you find that they can all be surmounted, that there is no fundamental reason why, if there is life on Mars, it couldn't travel to Earth inside a meteorite. Same the other way. If you have life on Earth, you will very soon get it on Mars because of rocks knocked off Earth that go to Mars. So there's been a two-way traffic between these two planets throughout their history. So we don't know whether life started on Mars and came to Earth, started on Earth and went to Mars, or maybe started on both independently. So the where part of that, the when part of the origin of life, we can say it established itself on Earth already by 3.8 billion years ago. The where part, we don't know whether it was Earth or Mars, just possibly could have been somewhere else entirely, but I don't think it's very likely. So I think it was either Earth or Mars. For my money, it was Mars. But the really tough challenge is the how part, which is what I want to come on to now. How did life begin? And the subtitle there gives it away. We haven't a clue. As I said at the outset, it's still deeply problematic how a mixture of non-living chemicals spontaneously transform themselves into a living thing. And the fundamental problem is easy to grasp. If we ask today, what is the simplest living thing? If we take the simplest bacteria, it's already stupendously complex. It's something of such enormous complexity that it's inconceivable that it would have arisen just in one go by some amazing chemical reaction. Obviously, there was a long and complicated sequence of processes going from a chemical mixture to this first living thing. But we have no idea what that chemical pathway was. Pretty much no idea at all. Now, it may be that we never know. Of course, if all this happened billions of years ago, all traces of that biogenesis could now be obliterated. It could be that however good our science is, we would never reconstruct the events in history which have now been totally erased from the record. We can't look in the rocks and see the step-by-step process that took place. So there's obviously a large amount of conjecture involved in this whole issue. But we don't have to know a blow-by-blow account of how the first living thing got put together. What we'd really like to know is, was it just a freak event, an incredibly unlikely fluke chemical accident that just happened to occur in one little corner of the universe, or was it an event that was almost bound to happen given enough time? In other words, is life something that emerges more or less automatically as a result of chemical self-organization and self-complexification, will be expected elsewhere in the universe, or is it a product of chance? And now here the story is interesting. When I was a student, the overwhelming opinion was that the origin of life on Earth was a freak event, so incredibly improbable, would never ever happen anywhere else in the universe. The chance versus law idea was encapsulated by Jacques Monod, a Nobel Prize winner who got his Nobel Prize for elucidating the details of the genetic code. And his point of view was that the origin of life was overwhelmingly chance. A man at last knows, he said, that he's alone in the unfeeling immensity of the universe, out of which he emerged only by chance. I think that book was published in 1972. So that was very much the feeling, that it was a fluke event, that life is not only very complex, but very specific in its details, and that unless you had precisely those details happening again somewhere else in the universe, that it was inconceivable that you would have life. So you see, a lot rides on this, because if life is a fluke, then there's probably only one planet that's got it. But if life emerges more or less automatically, then it's likely to be widespread in the universe. Now today the pendulum has swung the other way, and the mood is best summed up by Christian de Duve. He's a Belgian Nobel Prize winning biologist, and his point of view is that life is almost bound to arise wherever physical conditions are similar to Earth. Given another Earth-like planet out there in the galaxy, de Duve thinks that it's pretty much inevitable that life will occur on it sooner or later. So he calls life a cosmic imperative. It's built into the nature of the universe, something that is bound to come out sooner or later. So we have the pessimistic view and we have the optimistic view. The pendulum has gone from life is a freak, a unique freak, to it's everywhere in the universe. The curious thing is that during that period of time, our understanding of the origin of life has advanced almost not at all. So what we're dealing here with is just pure sentiment. We're dealing with a scientific sociological phenomenon, that in the past it was fashionable to say life is a freak, it's now fashionable to say it's widespread in the universe. The truth of the matter is we just don't know. Now, there's a lot that's riding on it, and in particular, one of the great questions of existence is, are we alone in the universe? Is there life out there somewhere? And we'd all like to know, is there intelligent life out there somewhere? Could it be that we're not the only beings in the universe asking these sorts of questions, but that we share the galaxy and the wider universe with other intelligent organisms? Obviously, if there is life around the universe, if there are many Earth-like planets and many planets with life, then there's a chance at least that there'll be many planets with intelligent life. So that's a nice idea, that we are living in a universe that is teeming with intelligent life forms. But we don't know. It's a completely open question. The one thing that we can be sure about, that Darwin certainly didn't know, and the younger Davies didn't know, it was not known when I was a student, is whether there are any Earth-like planets beyond the solar system. We're now pretty sure that there will be about 1 trillion Earth-like planets in our galaxy alone. And at this particular time, there's a space-based mission, a satellite called Kepler, was launched last March. It's out there now looking for extrasolar planets. So these are planets going around other stars, and particular interest is planets that are going around sun-like stars, and what we want is Earth-like planets going around sun-like stars, because they're the ones on which you would expect to find life of the form that we know it, if the Davies is correct. So this is an active area of the subject of astrobiology. Astrobiology is the study of the nature of life in an astronomical context, and in particular, whether there is life elsewhere in the universe. And one of the founding tenets of astrobiology is the Davies cosmic imperative, that life emerges readily in Earth-like conditions. And because Earth-like planets are believed to be common, therefore it's concluded that life is widespread in the universe. So this is sometimes called biological determinism, or the cosmic imperative again, but the laws of physics are somehow rigged in favor of life, that you just put matter in the top of the sausage machine, you turn the handle of physics, and the life obligingly comes out at the bottom. Unfortunately, the reasoning behind this is fallacious. So people will often say, life as we know it is made out of the most common elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, most common elements in the universe, and the building blocks of life, simple organic molecules, are found not just on Earth, not just in life, they're found in meteorites, in interstellar clouds, and so forth. So people will argue, because the stuff of life is common, therefore life is common. But unfortunately, this is a logical fallacy. It's a logical fallacy because it confuses a necessary with a sufficient condition. It's true that the elements I've discussed and the building blocks of life are a necessary part of the formation of life, but they're far from sufficient. And we have no idea what the conditions are that are sufficient for life. It could well be that there's a whole host of different conditions that need to be met. And because we don't know how life began, we simply can't say what it is. So how do we make progress? Are we just stuck? Do we have to admit defeat? That this is a problem that we're never going to understand? Well, I never believe in admitting defeat. And so, let's forget that. I'd like to know whether there are ways that we can test this idea of biological determinism, the cosmic imperative. Can we test that in some way? And there are a number of ways that people point to. Obviously, what we want to do is look for a second genesis. If it's the case that life will arise readily under certain conditions, then what we'd like is to find a second sample of life. The big problem about life on Earth, as Darwin showed us, we have this evolutionary principle. we have variation and selection. And we know that the variations are random, and the selection just depends on the conditions at the time. When we look at the history of life on Earth, it's very hard to untangle those features which are contingent, is the technical term, basically just accidents of circumstance, and those which are almost inevitable or law-like. So I'll just give you an example. Wings have evolved many times on Earth, and you just go outside this evening and look and you'll see the flying fish. It's one example of wings. Completely different evolutionary pathway from the birds or the bats or the insects. So wings have evolved many times for the simple reason that they're a jolly good idea. They solve a fundamental problem, and we can see why evolution would select for them. But let's take the other extreme, the elephant's trunk. Now, no doubt elephants are very proud of their trunks, but we think of them as a somewhat bizarre adaptation, an aberration that you would be unlikely to find anywhere else. If for some reason we were to wipe out the higher life forms today and come back, say, in another 500 million years, would you expect to find wings? I think the answer is yes. Would you expect to find trunks? I'm really not sure, probably not. And so the difficulty is, when you've only got one sample of life, you can't untangle the accidental features from the generic features. If we had a second sample of life, we could say something about which are the expected features and which are the accidents. Now, how would we go about looking for the second sample of life? Well, the first of these is SETI, the Search for Extraterrestrial Intelligence. The subject of another talk, I don't have time to go into it, it's the subject of my next book. It's 50 years old next year. These are the people who sweep the skies with radio telescopes looking for messages from alien civilizations. The hope is that out there is not only life, but intelligent life, and that the aliens are beaming messages our way. We just need to point the telescope in the right direction, tune into the right frequency, and get the message, and then we will know for sure that we are not alone in the universe and it's teeming with life. So it's a great idea, but obviously it's a needle in a haystack search without any guarantee there's a needle out there. The second thing is that we can look for evidence of life on other planets. Now, as I've mentioned to you, Mars isn't a very good candidate for an independent origin of life. If we find life on Mars, chances are it got there from Earth, or vice versa. So looking for a second genesis, which is independent of Earth life, means that Mars is not a good place to go. We want to find somewhere where life has started, let me emphasize this, from scratch, independently of life on Earth. So we need to go beyond the solar system to be sure of that. So one way is to look at extrasolar planets. Well, I've mentioned to you that Kepler mission is looking for Earth-like planets going around sun-like stars. In a few years it will have a catalogue of those, and then the next step would be to send into space some fancy space-based mechanism called the Terrestrial Planet Finder, TPF, which would have the power not only to study those planets, but the atmospheres of those planets in sufficient detail to be able to deduce the presence of substances that might betray that there is life on them. For example, oxygen and methane together in the atmosphere of a planet would almost certainly indicate that there is some life. These are substances that would react with each other, and if they're not continually replenished by some sort of biology, we wouldn't expect to find them. In principle, we could do that. If we get enough money for the Terrestrial Planet Finder, it would be possible to deduce from the spectroscopic studies of these extrasolar planets that there is some form of life on them. But that's a long way off. Go to Mars, I've already discussed that. Mars is compromised, it's not the obvious place to go. What about synthetic biology? These are the people who try to make life in the lab. Wouldn't that settle it? If someone can make life in a test tube, proverbial test tube, wouldn't we then have solved the problem of life's origin? After all, we can make it, doesn't that mean it's easy to make? Unfortunately, not at all. Because what we want to know is not, can you make life with a big budget, a fancy lab, a team of trained organic chemists, and in particular, a clear idea of what it is you're trying to make. In other words, intelligent design. So you've got a room full of intelligent designers, all with a clear goal of what they're trying to do. That doesn't help us understand how it took place out there in the grubby world of nature without any intelligent design going on. Mother Nature had no idea that she was trying to make life. It's something that just happened. And so if we can make life by intelligent manipulation, it doesn't show us that it was easy to make out there in the universe. The only exception to that is if we find there are many, many ways of making life, many routes to life, then it may suggest other places, other locations where life may have formed. But by and large, synthetic biology is not a lot of help. What about this issue that I've mentioned, that life started on Earth very rapidly once the conditions settled down? This is often cited, that life must be easy to make. Carl Sagan made this point many years ago. He said, well, no sooner was Earth ready for life than up it pops. So therefore, life must be easy to make. Unfortunately, there's another logical fallacy. We only have one sample of life at the moment. You have to be really careful in drawing statistical conclusions from a single sample. The point being that the reason we are focusing on life on Earth as our sample is because that's where we live. We've selected it by our very existence. And here we have this, again, this picture that the heavy bombardment carries on to about 3.8 billion years ago. Life seems to get going very quickly, suggests it's easy to make. But here we've got a longer term view. This is 4.5 billion years ago when the Earth formed. This is the present moment. This is the bombardment. Here's the first traces of life on Earth. So somewhere in this window, life appeared on Earth. But in about another 800 million years, Earth will become uninhabitable. The sun will swell up and get so hot that it will boil the oceans, and any prospect for life on Earth will be very dim. So there's actually only a finite window of opportunity, a few billion years, for life on Earth to get started. So unless it had got going pretty early on, it wouldn't have had time to evolve intelligence before the Earth sizzled. So the fact that we are here before doomsday means that life had to get going quickly. So we cannot conclude from this sample of one that just because it got going quickly on Earth means it's easy to make and will get going quickly on other planets too. So you have to be really careful with this reason. So now I want to come to my own contribution to this subject, which is to suggest a better way of testing this cosmic imperative idea. What is the most Earth-like planet we know? Well, it is, of course, Earth itself. So if it's the case, as astrobiologists seem to believe these days, that life emerges readily in Earth-like conditions, then surely it should have happened many times over right here on Earth. And so the next question is, how do we know it didn't? All of the textbooks will tell you that all life on Earth is descended from a common ancestor. Darwin gave us the notion, the metaphor of the tree. So the first living thing branches and branches and branches, and now we have many, many branches on the tree of life. What I'm saying is, how do we know all life on Earth belongs to a single tree and that there isn't a forest, or at least two trees? What we'd like is to find a second tree of life right here on our home planet. We don't have to go to Mars, we don't have to look to extrasolar planets. We might find an evidence for a second genesis right here on Earth. So that's led to a notion that we call the Shadow Biosphere, that in addition to the biosphere that we know and love, there might be a hidden one, hidden not because it's invisible, but because we just haven't noticed it yet, of an alternative form of life. Life on Earth, but not life as we know it. Now, obviously, this life would have to be microbial life only. We would have noticed any big life forms that were not life as we know it. So we're talking microbial life, but that's okay, because almost all known life is microbial anyway. The vast majority of species of our own type of life are microbes. And so far, less than 0.1% of all the microbes out there have been characterized, let alone had their gene sequence. It's a mystery zone. We don't know what all those little organisms are, and it's far too soon to say that they are all our form of life. So, along with some colleagues, we've been working on the idea of how we could detect evidence for a shadow biosphere. And the strategy falls into two. One is if there is, if the shadow life, so to speak, is ecologically separate from ours, and the other is if it's ecologically integrated. I'll just run through this briefly and tell. If If it's ecologically separate, what I mean is that there are places on Earth that are beyond the reach of life as we know it. And if we go there and we find that there is still some form of life, then that's a great place to look for life as we don't know it. Now, one place that people look for life is under the sea. And this is a picture of the submarine Alvin, which discovered the deep ocean, or inspected the deep ocean volcanic vents about 20, 30 years ago, and discovered entire ecosystems of organisms living around these so-called black smokers. So these are pictures of volcanic vents on the seafloor from which fluids are spewing at enormous temperatures, like 350 degrees, and the water doesn't boil because of the immense pressures of depth. And the dusky-looking fluids, it's not real smoke, it's precipitates of minerals which are dissolved in the hot water, and when it hits the cooler water surrounding it, they precipitate out and form these chimneys that look like black chimneys. And so these are now very much a feature of undersea exploration. And what one finds is that around these infernos is not just life, but an entire ecosystem living in total darkness deep beneath the sea. And so this is life which is sustained not by sunlight, but by mineral and thermal energy coming up from the Earth's crust. So this is life that looks downwards for sustenance, not upwards. This is now much studied. I'm not going to dwell too much on it for lack of time, but it's only the beginning of a very complicated story, because what you also find is that the life doesn't just cluster around these volcanic vents. We find it also when you drill down into the seabed, down to a depth of about 1 kilometre or so, in fact as deep as they've gone so far. This is a survey ship. It's an Australian survey ship called the Davies. And these people drill down into the seabed, return the rock cores, and what they find is that in this rock there are a huge number of microbes, bacteria and archaea, which are single-celled organisms which are genetically different from bacteria, but are likely to be even older than bacteria. The same is true on land. If you drill down into the continental crust, you find evidence for life down 1, 2, 3, maybe even 5 kilometers down under the ground. So we now realize that life on Earth is not restricted to a thin veneer on the surface, but in fact extends down into the crust. And so this is a picture of Tommy Gold, Cornell University, who championed this idea 20 years ago, and everybody laughed at him. He said there's life deep under the ground. Nobody believed him, but we now know it's true. And so here we have surface life, and these are the volcanic vents, but life also extending down into these regions here. What you find is that this life is living, a lot of it is living at very high temperatures. I mentioned the scalding effluent coming out at 350 degrees. Nothing's living at that temperature, but around about those volcanic vents at temperatures up to about 120 or 130 degrees, you find microorganisms thriving in those conditions. But all of those studied so far have been life as we know it. Even life in these extreme conditions is still life as we know it. Now, the high temperatures are only one of the extreme conditions. I mentioned that, extremes of heat. We also have extremes of salt. Extremes of salt, oh dear. Extremes of radiation. There are microorganisms that live in the waste pools of nuclear reactors. They're so radiation resilient. Keep doing this. There's extremes of cold. The Antarctic dry valleys. There are microorganisms that can live in conditions that are never above the melting point of water, and extremes of dryness like the Atacama Desert. Then last but not least, there are extremes of what I call yuck, chemical contamination, and organisms that live in heavily contaminated mines and tailings of mines and so on. Collectively, these organisms are known as extremophiles because they live in extreme conditions. All extremophiles so far studied are life as we know it. But there are limits. And so if we look at conditions which are beyond the reach of even the hardiest extremophiles, and we find something living, then that's a good candidate for life as we don't know it, some alternative shadow life. More interesting but much tougher is the idea that there is some alternative form of life on Earth, but it's intermingled with life that we know. So these will be ecologically integrated microorganisms. And then the challenge is how to separate the sheep from the goats, how to figure out among all these microorganisms which is life as we know it and which is some other form of life. And the best way of doing that is to filter out all known life and see if anything is left. Another way is to just guess what an alternative form of life might do, and to go out and look for some sort of biomolecule that it might be using. Just give you a couple of examples of both before coming to my conclusion. One of these is that all life is based on molecules of a particular handedness. So an amino acid, for example, would always, incorporated in life, would always be a left-handed amino acid. But in a mirror, it would, of course, be a right-handed amino acid. The laws of physics make no distinction between left and right. So if life were to start all over again, it may well pick the opposite hand next time. So instead of having life with left-handed amino acids, it might have right-handed amino acids. And instead of having right-handed sugars, it might have left-handed sugars. It may be made of DNA, but instead of the DNA being a right-handed spiral, it will be a left-handed spiral. And so this raises an interesting idea. Supposing life started again on Earth, but picked the opposite hand next time, that this would be a sort of mirror life. It could coexist alongside ordinary life, and we wouldn't notice it. So Pauline had the idea, well, why don't you search for this life by getting a nutrient medium of the opposite molecules. You can buy this stuff commercially. You make a bowl of anti-soup, and you see if anything grows in it. The point being that life as we know it will struggle to digest this anti-soup. It wouldn't really like it, but mirror life will positively lap it up. And so we persuaded a couple of people at the Marshall Space Flight Center, Richard Hoover and Elena Pacuta, to do this experiment. So they did a pilot experiment in which they bought the chemical constituents of anti-soup and the ordinary culture medium of soup, and then they tested their favorite microorganisms to see if any of them would grow in this mirror soup. And remarkably enough, they found one. They did. However, it turns out not to be a totally radical new form of life. It's simply an organism that has, for some mysterious reason, the ability to metabolize the anti-soup. So this is work in progress. The last idea I want to tell you about is the possibility that life as we know it that if there is some alternative form of life, one of the fundamental elements on which life is based, remember the carbon, nitrogen, hydrogen, oxygen, phosphorus and sulfur, that one of those might be replaced by something else. Not carbon, I think. I think everybody agrees that all life must be carbon-based. But one of the others could be replaced by something else. And the favorite one is that phosphorus, which is rather rare on Earth, might be replaced by arsenic, that arsenic could do the job of phosphorus. I should say right at the outset, it's not my idea. It's the idea of former postdoc of mine, Felisa Wolf-Simon. She's now at Harvard University, and she has a research grant to go look for arsenic life. And the place she's looking is here. It's Mono Lake in California that's heavily contaminated with arsenic. And here she is with Ron Omland from the US Geological Survey, and they went out there a few weeks ago, and they took samples of life from the sludge at the bottom of the lake, and they're culturing them in the lab, and here they are. And what they're doing, this is like something out of an Agatha Christie novel, that they're taking these organisms and they're giving them more and more arsenic and no phosphorus. And then you would expect at some stage life as we know it to simply expire, whereas if there is some arsenic-based life there, it will live on. It's too soon to announce the results of this. All I can tell you is it looks deeply intriguing and very exciting, and if they have really found arsenic life, there'll be a Nobel Prize in it for sure. But it's too soon to say that this is the case. So this is just work in progress, but within a few months, I think we'll have a better idea of what lurks in Mono Lake, whether it is an alien form of life or whether it is simply another extreme form of life as we know it. And so this leads ultimately to the question of how do you know, if they find something, that it is genuinely an independent origin of life, or whether it is simply a hitherto unknown branch on the known tree of life. But the problem is, when is a root a branch? You think you're dealing with two trees of life, but you find that further back and deeper down, they're actually joined together. So this is a picture of the tree of life as we presently understand it. They've got three great domains. Here are the bacteria, here are the eukarya, the archaea, as I mentioned to you, and the eukarya. All multicellular life is part of this eukarya. We're in here somewhere. Here we are, Homo, along with yeast. We're in nearby. And you see that we're as different from the archaea as the archaea are from the bacteria. These are all single-celled organisms, and all multicellular life is in here. So we need to be sure, if we find some truly novel form of life, that it represents an independent tree or independent bush of life, and not just some exotic fourth branch on this known tree here. And that may be very difficult to establish, because we need to be sure that life started in a fairly well-defined way for us to be able to say that there were separate origins. So these are issues for the future if we ever get around to discovering some radically different form of life, some life with a totally different biochemistry. So the conclusion is that if Earth has had in the past some form of shadow biosphere, then life will be widespread in the universe. It would be inconceivable that life has started twice on Earth and never anywhere else around the galaxy. That shows us that life will be a fundamental, and therefore, in my view, a significant cosmological phenomenon, as opposed to some trivial, irrelevant little aberration, some byproduct that's just some quirk that's occurred in some remote corner of the universe. In other words, it'll be a truly cosmic phenomenon. So we will then not be freaks, but as it were, an expected part of the outcome of intrinsically bio-friendly laws. We will, to use the expression, I think, feel at home in the universe. So I think the philosophical consequences as to whether we live in a universe which is pointless, absurd, and in which human life is part of some meaningless procession of random events on the one hand, or whether on the other hand we live in a universe that's got some sort of cosmic scheme, something like meaning or purpose, hinges, I believe, on whether or not we live in a universe in which biology is universal, or a universe in which it's restricted just to here on Earth. So I think that the search for the shadow biosphere is, in a sense, a search for ourselves, who we are and how we fit into the great cosmic scheme of things, which is why I'm so excited by the prospects that we might actually find this shadow biosphere within a very short period of time. That's all I have to say. Thank you.